A very good afternoon to all of you. And proceeding from our previous discussions, as we have been talking about variational principle in general, and we have uh, we have we have tried to solve the problems based on variational principle in the past, and we chose the problems that are exactly solvable, where it's not cumbersome to choose a trial wave function. So here, what we have been doing is, now we will take on our discussion to the next level using the same approach, so that a state of confidence building happens here. So in the previous video, we talked about uh, the ground state of one-dimensional harmonic oscillator problem, and we solved it by choosing the exact trial wave function, because the wave function is exactly calculable for the ground state of harmonic oscillator, one-dimensional harmonic oscillator, and the same thing is true for the first excited state of the harmonic oscillator. So in this video, what we'll be trying to do is we'll try to use the same approach in calculating the energy of the first excited state of the harmonic oscillator. And what is important at this point is that the calculations that would be carried out on the excited state are purely dependent on the calculations that have been executed in the ground state of harmonic oscillator. And the trial wave function that should be chosen here, this wave function should be orthogonal with respect to the wave function of the ground state of the one-dimensional harmonic oscillator. So is the case with the energy. So there has to have the orthogonal. One has to keep in mind, one has to bear in mind that the trial wave function that's chosen has to be orthogonal to the trial wave function that has been chosen for the ground state of the harmonic oscillator. Now, the first point of contention here is that we will be using exactly the same exact wave function that we have for the first excited state of the one-dimensional harmonic oscillator. And what is important here is that in this problem, what we have, since we are talking about the first excited state of the harmonic oscillator, so there is a need to have a trial wave function in which we will have one node. As was the case when we talked about the ground state of harmonic oscillator, we chose a trial wave function where we don't have what we call as we don't have any node. So at that time, we chose a trial wave function of that nature. So here, when we talk about the first excited state of a harmonic oscillator, what we have to choose the trial wave function, which I'm taking exactly as the wave function that's exactly known for the ground state of harmonic oscillator. Now let us choose that as, say, a x e to the power of minus, say, some zeta x square. So this is our trial wave function. So choosing this as trial wave function, A is a constant, zeta is an adjustable constant. It's an adjustable constant. And we have an exponential function, and this exponential function is multiplied by x. Now, what is important here is that if we rightly go back to the ground state of harmonic oscillator, we were talking about an even function. So even function means when you replace the function, say x, by the negative of the x, the sign of the overall wave function should not change. So if the sign of the overall wave function changes by changing the sign of x in our trial wave function, then this wave function has to be it has to be an odd function. So this is the necessity of dealing with the first excited state of harmonic oscillator, and the necessity is that the trial wave function that is chosen has to be odd, so that the condition of orthogonality is purely resolved, because the wave function in the excited state should be orthogonal to the wave function in the ground state. Now, if we have chosen this state vector psi as an odd function, so we can check whether this function is odd. And what is another important point here is that we must be able to obtain a node. In addition of obtaining a node at infinity, we must be in a position to have a node for this function. So for getting a node, what is important is that the state psi has to be equal to 0. So in doing so, the trial wave function, that is ax e to the power of minus zeta x squared, must be equal to 0. But one thing is clear, that this a is something that's to be calculated by exploiting the normalization condition. So a is a constant, it cannot be equal to 0. So what should be equal to 0 is x e to the power of minus zeta x squared. So this whole thing must be equal to 0. But this thing, the value of this exponential is not 0 at every point. So we can see here that if I choose x equal to 0, then certainly this whole function will be equal to 0. So this is giving me a node that I was searching for. So what's a node? A node is a point in a vector space where the amplitude of the state vector is 0. So the opposite of the node is an antinode. An antinode is a position where the amplitude of the state vector is maximum. So this is one point. So at x equal to 0, we will have a node. So the psi, the state psi, will be equal to 0. And again, we can have both x equal to plus minus infinity. At these two values, again, the value of this state vector is going to be equal to 0. And one more thing, we can exactly check out whether this function is odd or even by simply replacing this x by the minus x. So if we do that, we can see that, okay, there will be no change in the exponential function because we have the square of x, but it's multiplied by this x. So if I replace x by minus x, I'm going to get my state vector equal to negative, my function equal to the negative of the whole function. So that gives the confirmation that the wave function, the state vector that has been chosen over here, is this function is an even function. So the first thing that we can look for here is to calculate the value of this normalization constant, and the procedure is exactly same. Now let's do a little bit of exercise, and then I will leave the results on you. You can do the calculations, and you can finally calculate the energy of the first excited state of the harmonic oscillator. And what we have been choosing the symmetrical problems, and symmetrical problems, they are very bright examples to understand the complex system as well. So what should we do now? We should use the normalization condition. The normalization condition to calculate the value of A. So So what I have the state of psi, and this psi is ax e to the power of minus zeta x squared. Now if I take the bra of this psi, since there is no iota involved in our trial wave function, the bra will also be the same thing, ax e to the power of minus zeta x squared. Now, in order to use the condition of normalization, what we'll have to take the inner product of this bracket. So psi and psi, this inner product must be equal to 1. So that's the case. So proceeding from here, what we can do is we can look for the bra. So this is a e to the power of minus zeta x squared, then a e to the power of minus zeta x squared. This has to be equal to 1. Now let's write down this bracket in integral form, and in doing so, what I will have an integral from minus infinity to infinity. A e to the power of minus zeta x squared, a e to the power of minus zeta x squared is equal to 1. So a and a will give us a squared. So inside we have minus infinity to infinity. Then I'll be getting, so I forgot to write x here. So x has to be here in our trial wave function. X has to be here in our trial wave function. And what we'll get is, we'll get x squared e to the power of minus, so bases same powers added will give me zeta x squared 2 times zeta x squared dx is equal to 1. And now what we have to do is we have to write down the value of this integral. And once we write down the value of this integral, we will be able to calculate the normalization constant. So what I'll have is a squared integral minus infinity to infinity. Then I have x squared e to the power of minus 2 zeta x squared dx. This thing is equal to 1. Now what I have integral minus infinity to infinity, then x to the power of 2n e to the power of minus, let me go with minus alpha x squared dx. Now this is equal to 1 dot 3 dot 5 so on and so forth, 2n minus 1 divided by 2 alpha whole raised power n under root of pi by a. So what will be the value of our integral? This is going to be a squared times. Now for this integral I will have n equal to 1 because we are talking about the first excited state of the harmonic oscillator. So for that I'll be getting x squared here. For n is equal to 1, I'll have x squared, and certainly 2n minus 1, this is the term up to which you have to go here. So for n is equal to 1 will give me 1, so this is 1, 1 by 2, 1 by 2. So instead of 2 alpha, we have 2 zeta. So 2 times 2 zeta whole raised power, n is only 1, so it will remain like this, under root of pi by alpha is 2 zeta. This is 2 zeta. This is equal to 1. So from this equation, what we can do is we can calculate the value of this a. So we can do that. So what we will have is, we will have a squared equals, this is 4 zeta, if you go up, and under root of 2 zeta divided by pi. Okay, this is our a squared. And we can insert this 4 zeta inside this square root. We can do that. So a squared will be, this will be under root of, so 4 will go inside, it will make 16, and zeta will go inside, it will make zeta squared, and we have our own 2 zeta inside divided by pi. So A square will be, A square is going to be under root of 32, then zeta cube divided by pi. So we can write down this A as 32 zeta cube divided by pi, and whole raised power, it has its own whole raised power 1 by 2, and this 1 by 2 will be multiplied to the another square of root, so this will be 1 by 2. So what we will have is, we will have A equal to 32 zeta cube divided by pi raised power 1 by 4. So this is the value of the normalization constant that we were looking for, and we will try to calculate. Now the next thing is, what we have to do is we have to calculate the expectation value of the first excited state. So expectation, we are assuming that our state vector is normalized, okay, and the expectation value of first excited state of one-dimensional harmonic oscillator. So what will be that? That will be simply E. So let me call the first excited as, say, E1. So that's going to be expectation of psi, h, and psi. So h is an operator here. And we have presumed that psi and psi, the inner product of the two psi's is equal to 1. So I'm not taking into account the denominator of this expectation value. Now, what is important here is that that this H operator is the Hamiltonian operator for one-dimensional harmonic oscillator. So for that, we will have the kinetic energy part, that is minus h bar square by 2m. And then since it's a one-dimensional problem, so you will have the total derivative with respect to x, then plus the potential energy part will be 1 by 2 m omega x cap square. So we have the kinetic energy operator here, and we have the potential energy operator here. And at the same time, we understand that if we take a position operator on the state vector, it always leads to the position. So what should we do is we should inculcate this Hamiltonian operator in our calculation of the energy expectation value. So in doing so, what we'll be getting this E1 expectation. It's going to be the state for the psi. I will have ax e to the power of minus zeta x square. Then you will have the Hamiltonian. Come on. You will have the Hamiltonian operator, and what is that? Let me choose this minus h bar square by 2n. Let me choose this as, say something like, let us assume it to be small a, so that it doesn't create a much of problem to be inside. So let me call that a. Then I will have d2 by dx2, and then I will have again ax e to the power of minus zeta x square. Okay, I will close it. There will be another part of it, that is ax e to the power of minus zeta x square, and here I'll have, here I called it a, and I have taken a is taken as minus h bar square by 2n, and let me take b as 1 by 2 m omega square, 1 by 2 m omega square. So we can do that. So here I will write b x bar square and then ax e to the power of minus zeta x squared. So we'll have two parts to be calculated. The first part will go with the kinetic energy part of the expectation value, and the second part will give us the potential energy. You will have the numbers, you will add the two numbers, and you will get the expectation value. So we can write down this part in integral form, and so I will be writing this as E1 is I1 plus I2. So I'm referring this part as I1, and I'm referring this part as I2. So let us look at least mathematically how does they look, and how to calculate these integrals. So in doing so, we will have the part 1. For the part 1, I will have I1. So I1 will be an integral from minus infinity to infinity, and we will have ax e to the power of minus zeta x squared. Then we will have the double derivative, and then again we will have ax e to the power of minus zeta x squared. And this is the thing that we have to evaluate, and this is multiplied by small a. We should keep that thing in mind. Okay, so this is equal to, so what I have to do is I have to take its first derivative, then I have to take its another derivative, and then I will have to substitute that thing in my integral. So in doing so, what's my d by dx of this? So I will take the first derivative. So the d by dx of a is to be multiplied. So you will have capital A square outside. This capital A square will be outside the integral. Get it out. So inside I will have I will take the first derivative of this. That is x e to the power of minus zeta x squared. So what will be that? For that, x as its, the derivative of the second will give me minus 2 zeta e to the power of minus zeta x squared, and then plus e to the power of minus zeta x squared into the derivative of x, that's equal to 1. So this is the first derivative of this trial wave function that we have. So what is it? Let me write down this. So it is something like, so this is minus 2 zeta, and then you will have times, okay, then you will have times x e to the power of minus zeta x squared. Okay, this is an independent term. Yeah, this has to be an independent term. And then we will have plus e to the power of minus zeta x squared. Now what I have to do is I have to take another derivative of it. So in taking another derivative, again here I will have, I might have committed some mistake, I think so. Something is, so this is 2 zeta x. So the internal derivative of the exponent is 2 zeta x. So this is zeta here. So if it is zeta, so it's going to give me the x squared. So here I will have x squared, and then in this case I will have the only exponential function. So I would like to differentiate it again. So let me differentiate this thing again. So if I have to differentiate this again, so minus 2 zeta will be like this. Now again I have the UV rule, so this is my u and this is my v. Okay, so u as its into the differentiation of v is minus 2 zeta x e to the power of minus zeta x squared. Then again you will have plus e to the power of minus zeta x squared will remain as its, into the derivative of x squared is 2x. So here I'm going to get 2x. And then I have this exponential function plus uh, it will remain as the exponential function e to the power of minus zeta x square, and you will multiply this thing by 2 zeta x. Fine. So what we have is, these are the results that we have obtained till now. So we have taken the derivative of this this function as uv, and here we have only, it has to be x, because I'm seeing, what am I doing? This x is common, so this exponential function has to be multiplied with x. So here again I'll have the uv. So here I will have the uv again. So how can I do that? So this term, let me rub it for the time being. Okay. Now in this case, what I have plus. So x as x into the differentiation of this thing will give me minus 2 zeta x. And then you will have e to the power of minus zeta x squared, and then plus e to the power of minus zeta x squared as x into the derivative of x, that is equal to 1. So here I will have only e to the power of minus zeta x squared. So I'm not sure, I might have committed a mistake, I'm not sure, and now let us see. See, even if I have committed a mistake, that's a beautiful thing. We learn from mistakes alone. We can't learn the things by spoon feeding, and you can fix that. Now the point is, I will go inside, I'll be going inside this, inside the whole thing. So 2 zeta is out for everything inside the brackets. So do we think that we can add something? So this is minus 2 zeta x squared, okay? And here you have e to the power of minus zeta x squared 2x. Okay, so this is 2x. So moving from here, what we'll be getting is, let's go on. So this will give me minus 2 zeta x, this will give me minus 4 zeta x cubed. Minus 4 zeta integral minus infinity to infinity. Why am I using the integral here? Okay. No. This is minus 4 zeta x cubed e to the power of minus zeta x squared. This will be the first term. Okay, so this thing, now 2 times 2 will give me 4. This is minus 4 zeta x. Now I'll have minus 4 zeta x e to the power of minus zeta x squared. Right? So this is minus 4. So this thing is multiplied. So this will give me, it has its own minus, and minus, they will become plus. So this is 2 zeta squared x squared. So plus 2 zeta squared x squared, and then the exponential function e to the power of minus zeta x squared. And the last term, that will give me minus 2 zeta e to the power of minus 2 zeta e to the power of minus zeta x squared. Now these are the things that we have obtained till now, and I would like to stop here, and I would like to proceed this calculation in the next lecture.